Thanks for your patience again. And it's about due time. And the sixth speaker of this session is Stephen Holtzen. And he's going to talk about scaling optimization over uncertainty via compilation. Let's start.
All right, thank you so much for the introduction. So this was work done by Minsung and John. Unfortunately, neither of them could be here to present, so I'm going to tell you guys all about the awesome work that they did. Oh, that's not showing. Okay, that's fine. We'll do it this way. All right, so what is modeling? Okay, so let's start with uncertainty, right? So we need to talk about what it means to model things with probabilistic programming languages, okay? So probabilistic programming languages make it possible to express rich probabilistic models, right? So the idea, like for example, let's talk about medical diagnosis, okay? So in medical diagnosis, you're a doctor, you want to diagnose a symptom with some diseases. So what you would do is you would say, okay, I think an average person in the world has a cold with 10% probability and a flu with 20% probability, and I would say that by having coin flips in my programs, right? And then I'm going to relate the symptoms and the diseases. So I'll say I have a cough according to some maybe complicated function that relates those diseases to the symptom cough, right? And similarly for fever and dehydration. And then the doctor, when they're trying to do their diagnosis, would observe. They would say, aha, this person has cough and a fever, and then they want to know what's the probability that they have a cold, right? This seems very useful and helpful. Maybe another example that'll be interesting is network diagnosis, right? So maybe I'm in a situation where I'm trying to diagnose the probability of a packet reaching the end of a network, right? And each link in the network has a failure probability, and I would annotate that. So like there's a 8% chance that the link from R1 to R3 fails, and I want to know, will a packet get to the end of the network? And I can again encode this situation into a probabilistic program where I've kind of modeled the router links failing with coin flips, right? So I'll say the R1 to R2 link fails, or is there with 96% probability, and then I can model the routing protocol as a probabilistic program, so I would choose to go up or down with some coin flip and so on. And then the program will tell me the answer to this question. Now, I want to tell you what we're pretty good at, right? So we're pretty good at inference. So inference is computing the probability that a probabilistic program outputs a particular value. And I would say we have this kind of boiled down to a science at this point. We've been working on this for quite a few years. So here's that router example, and I would run my probabilistic programming language, and out would come a number. It would say, okay, the probability of outputting true is 0.926, and it would do some algorithms to kind of figure this out for me. And we have many inference strategies. You could write long textbooks on these things. There's different kinds of exact inference, sampling, Markov chain Monte Carlo, importance sampling, generating functions, and so on. There's lots and lots of things. So I'm here to kind of tell you about the things we should be doing next, right? I think we should be thinking more about questions that go beyond inference, right? And I think that there's two in particular that I want to tell you about, marginal map and decision making, okay? And they're both going to be very similar questions. They're going to be solved with very similar methods, but they're very interesting and compelling kinds of questions. So what does the doctor really want to know? Given some observation of symptoms, what is the most likely underlying disease, right? They want to do diagnosis. They want to know what the most likely underlying disease is. So one thing you could do is you could return the joint probability distribution on both the cold and the flu. And if you did that, out would come like a histogram, right? And it would say, okay, well, here's all of the possible joint configurations of those diseases. And you know, I'd just pick some numbers here just to give you a visualization. And then if you're doing diagnosis, the doctor would say, aha, okay, well then the most likely configuration of these variables jointly is this histogram here, which has a probability of about 50% of the patient not having a cold and not having a flu, okay? Now we kind of can boil this question down of finding pretty much the highest bar in that histogram to something called the marginal map task, which is to compute the most likely joint assignment to a subset of variables, right? So it turns out that this marginal map inference task is extremely hard. It involves, you can kind of see why, right? Like I would have to compute each of those histograms, each bar in that histogram, and each bar is itself an inference task, right? That's computing the probability of something about my program. So it seems like I'd have to do that exponentially many times, one for each possible joint assignment to the variables over which I'm optimizing, right? And that's very hard, and we can actually say that it is NP to the PP hard. So it's hard if I have a counting oracle, and that's pretty spooky. And so, you know, and there's an intuitive reason for this hardness. It seems to entail somehow enumerating over all the models of that. Okay, so that was marginal map, finding the most likely joint assignment. So there's another kind of task you would do that has a very similar character, which is optimal decision-making under uncertainty. Right? So back to this router example, suppose a router goes down, and the network admin needs to find which router failed, and is rewarded for finding the failing router sooner, so they have to kind of sequentially investigate. And so the goal is to find a policy for investigating the routers that has the highest expected reward, right? So you want to kind of come up with a plan here in order to kind of solve this problem. So languages that can model such tasks are called decision-theoretic probabilistic programming languages, and there have been a couple of them before. And the idea is that they have actions, rewards, and randomness in them. So I want to show you an example. So here's a smaller one than the router one that's easier to wrap our heads around. So I'm trying to decide whether or not to bring an umbrella, right? This is very relevant for us here today in Singapore. Every day there's been rain in the forecast, so do we bring our umbrella, right? So you have some probability of there being rain, and then you have a choice whether or not to bring an umbrella or not, whether to bring an umbrella or not to bring an umbrella, right? And this is like a keyword in the language. It's a non-deterministic choice of these two possible actions, right? And so then I have two things that I would do, depending on which action I chose. If I bring the umbrella, then if it's rainy, then I get a reward of 10. I blocked the rain, and if I didn't bring the umbrella, then I get wet. I'm sorry, if I brought the umbrella and it didn't rain, well then I brought an umbrella for no reason, so there's a minor penalty for carrying the umbrella, I guess. And then if I don't bring the umbrella and it rains, then I get wet, and that's very bad, right? And I can compute kind of the rewards of these two policies by kind of taking the weighted average over those outcomes and weighting the reward by how likely each outcome is. And you can see that if I bring the umbrella, that has an expected reward of negative 3.5, and if I don't bring the umbrella, then it has an expected reward of negative 10. So if you're the kind of person that optimizes for that kind of expected utility, then you would choose to bring the umbrella in this situation, right? So again, we're in a situation, so we want to find the optimal policy, and it's kind of like a similar situation where I have a potentially exponential search over all of the possible actions and policies I might choose, which again is this kind of NP to the PP, searching over a space of possible choices kind of situation. And it is again NP to the PP hard to solve this problem. So what did we do, right? So you know the problem now. So we're going to give you two new programming languages for modeling these kinds of tasks. They're discrete and they're loop-free, so they're kind of small and contained, but we're going to try very hard to solve these very difficult reasoning tasks on them, right? One of them is going to be called dappl. It's a decision-theoretic probabilistic programming, and it's going to have first-class optimal decision-making. So you can query in the program for the policy, and you can kind of use that as a value if you like. And then the other one is pineappl, which has first-class marginal map. And we were kind of curious to see what the language design of these things would look like. And kind of the key idea that I think we bring in this paper is that we have a branch and bound based search strategy built on knowledge compilation that can solve these two problems. And really the point is that we're going to amortize the cost of repeated inference by compiling once. The idea is that we're going to do some very expensive analysis that makes inference fast, and then that'll make our subsequent search much faster because we've kind of amortized that inference cost by doing this compilation, okay? So then we're going to furthermore kind of generalize this branch and bound search to work over what we're calling a branch and bound semi-ring, which will let us deal with the decision theoretic stuff. I'm not going to have much time to talk about that, but there's a lot of detail in the paper on that, and if you care about that, it's there for you. And the point, I guess, is that the same algorithm is going to be used for solving both. You're just going to be able to pick a different semi-ring, and then in one semi-ring you're doing optimal decision making, and the other you're doing marginal map. Okay, so it's the exact same Rust code doing both. And this is going to be state-of-the-art performance. It's going to go pretty fast, and I'll show you some experiments hopefully if I have a moment at the end. Okay, so I wanted to give you a flavor of this approach so you could see what we're doing and how we're solving this kind of difficult optimization task. And here's our pipeline. So we're going to start with our programs on the left, and then we're going to compile them into this semi-ring weighted Boolean formula. And this step is fairly fast. It's kind of like doing a SAT where you kind of take your program and you turn it into Boolean formula first. That's not usually too slow. And then step 3 is going to be quite expensive. We're going to take this semi-ring weighted Boolean formula and we're going to turn it into what we're calling a branch and bound intermediate representation. But if you like, you can think of it as a BDD. That's what we're going to have in that spot. So you're going to do some kind of BDD compilation happening here. And that's going to make inference linear time on that BDD. And that's going to be kind of our edge. And then we're going to kind of do repeated search on that BDD that we compiled. We're going to repeatedly query it a whole bunch of times. Each of those queries is linear time, right? That's kind of how we're getting our speed up. And then finally, out comes our answer in the end, because we'll do that search and we'll find the optimal assignment. Okay? So I wanted to give you a really kind of concrete, tracing a drop of blood through that flowchart so you really understand what we're doing there. So we're going to compile a program into this weighted Boolean formula for step 1, and I wanted to give you an example program that we're going to be talking about. We make the program smaller and smaller, so this one only has 2 coin flips. X, which is a fair coin, true with probability 1/2, and then Y, we can join X onto another fair coin flip, which is true with probability 0.2. And then let's say we're optimizing Y, just to keep things nice and simple. Okay. So first we're going to get out a Boolean formula for this, and kind of the way we choose this Boolean formula is very important. It's very carefully constructed to work with the subsequent steps. We have a variable x here, and then it's true if and only if f1 is true, and we introduce this f1 variable, which is going to be the weighted variable. Okay, that's where the probability is going to live. And then y is true if and only if f2 is true and x is true. So maybe you can start to see already how this formula is kind of capturing all of the joint assignments to the variables in the program x and y. And then alongside that formula, we're going to have this weight table, which is going to associate every literal, so every assignment to every Boolean variable, with a weight. So that's a number, and that weight is what's going to change to be a semiring in the paper. We generalize that weight to be semirings. Here, we're just going to do real numbers, and that's what they are. So you can see x is 1 and not x is 1, so it's not really going to be contributing anything to the weight. And then f1 is 0.5 and not f1 is 0.5. And then to get the weight of the model, we take the product of the weights of the literals, so you product these guys up, and that's kind of how we associate the weight of a model to a run through the program. Okay, just kind of speeding through here, but I think it's easiest to see on this picture. So then we're going to compile this weighted Boolean formula into a binary decision diagram. This is going to be kind of expensive, right? Getting a BDD out of a formula we know is expensive, so we'll get one out. It looks like that. So we kind of can see how this tree has x at the root, so I've picked a variable order, and then if it's true, I go this way, if it's false, I go this way, and then I kind of have all these trees together. You can see how I've put the weights on the BDD, right? So you can think of this as like a weighted BDD where I put weights along each of the edges, right? So then I'm going to give you a very naive algorithm for solving marginal map. Now that you've built this BDD, we're going to enumerate all of the possible assignments to y and do a bunch of passes up this BDD. So how does that look? So let's try y being true, okay? So if I make y true, I kind of get a sub-BDD. I've gotten rid of all of the paths through y that are false, and I kind of have this BDD here. You can see how these y variables no longer have their false branch, right? I've gotten rid of that. And then I can do a pass up this BDD called weighted model counting. And I kind of start from the roots and start from the leaves and I work my way up. So true is 1, false is 0, and then I take the weighted sum of the leaves to get that, and so on up the BDD until I get 0.4. Okay, and we've set this up very carefully so that this weighted model count corresponds to the probability of the joint assignment over x with y being restricted to true. So that's part of our reduction. If you want to, there's a proof in the paper for why this is correct, but hopefully this is just to kind of get a feel for what we're doing. Okay, and then you can compare, and then you can also get the false value and kind of compare the two to know which one is greater, right? The problem with this, of course, is that it's exponential in the state space of the marginal map variables. We've still won, right? This is better than like doing a bunch of inference queries from scratch, but you still have to kind of exhaustively enumerate over all of the possible joint assignments to what you're optimizing over, right? So we can do better. So I'm going to give you kind of like improvement 1, improvement 2, and I won't have time to give you all of them. So you'll get as many improvements as you want, and if you care, you'll go find the rest. One thing you could do is reorder the BDD, and I think this is very clever. You can put the optimization variables first in the BDD order, and we didn't come up with this. There's a citation there, and it's all over the paper. You can check that paper out. Instead of performing a sum on the variables you're optimizing over, you perform a max over those variables, right? Let's see what happens if we optimize x on this BDD. So I do this weighted model counting pass up from the bottom all the way up to the root. And then at the root, instead of taking a weighted sum over the children, I take the max over the children, right? And you can kind of see how that would be computing the maximum assignment to that variable. And that seems nice because that's linear time, right? I just solved marginal map in linear time if I'm able to move all of the decision variables up to the top of the order, right? So that's an algorithm that might be better than enumerating over the possible assignments of the marginal map variables. And that can be very nice, right? Now, the downside to this approach, if it works, it's great, like all of these things. But you need to move the variables to the top, and that can blow up the size of your BDD. What happens if we don't reorder? Well, it turns out that gives you an upper bound. So I love when doing the wrong thing is still useful. And here, if you don't bring it up to the top, you get an upper bound. And that's the key idea. If you can see how you get an upper bound if you don't bring these up to the top, that's our whole idea. we make that work for semirings. So this turns out to be pretty fast. So we're able to solve some instances with 500 random variables. So that was all that I wanted to kind of tell you about. Hopefully you got the key idea of what we're doing. And if you have questions, please come find me. I'm happy to tell you more about what we did. Thank you so much.